and Junit and Sean, please come up. And of course, we had all of these all set up to go. That's my computer went out.
Thank you so much, Chris. That was an amazing talk, right? Wow. Wow, and thank you all so much for coming. This is such a great crowd. So here at Carnegie, we have been exploring a number of machine learning algorithms and advanced visualization techniques to better understand the types of data that we're looking at, and also to address big outstanding questions in Earth and planetary science. So today I'm going to talk about just one of those techniques, and that is network analysis. Chris mentioned that there are, he explored a number of ways to look at all of these three-dimensional data and touched on a little bit of multi-dimensional data. And that's really why we were interested in network analysis, because it allows you to view multiple dimensions at one time. So some of the questions that we're interested in answering, or the goals that we're trying to forward, is to document the diversity and distribution of minerals and fossils on Earth, to compare the mineralogy of different terrestrial planets and moons, to understand Earth's co-evolving geosphere and biosphere, and to discover previously unknown minerals and fossils. So let me talk a bit about what networks are. Networks are graphs. They're composed of nodes and links between these nodes. In our case, nodes are mineral species, or they are fossil genera, but they're any entity in a system. And they are connected by links. And in our case, this is coexistence of fossil species, or this is coexistence of two mineral species on Earth's surface. And these links and nodes come together to form a network. And so here we're looking at a network. This could be mineral coexistence, or it could be fossil coexistence. And the really interesting thing here is we can look at many, many dimensions at once, many nodes and links between them. But what we can also do is overlay a number of attributes. So we can overlay a number of parameters, up to about 7 on a network. And these are things like age, abundance, chemical composition. And we do that by varying the color of the color, the shape, the size of the links and the nodes within the network. So let me show you an example of a natural network. So a rock is essentially a natural network of minerals. This is a picture of a granite. Many of you guys have this in your home, in your countertops. And this is a network of mineral species. And those mineral species include things like quartz, orthoclase, albite, and biotite. And they come together to make up this rock network, if you will. So we can compare this rock network of minerals to that of other types of rocks. So here we're looking at a network of minerals. Each one of these nodes represents a mineral, and igneous rocks. Igneous rocks are rocks that form due to the cooling of magma. And we can overlay our granite here. So this is what our granite looks like. These are the minerals that make up a granite. And so you can see this is in network analysis. We call this a clique. It's a group of connected nodes. And we can overlay other types of rocks, so things like an olivine basalt, a nepheline syenite, and this allows us as researchers to actually compare the similarities and differences of these rock systems, and to be able to make some scientific inferences there. You'll see some rocks share minerals, some of them don't, and that can be really useful information. So another type of network is, this is a trilobite network. So trilobites are a type of fossils, and each one of these nodes represents a genera. I'll pop up some pictures here for those of you that are unfamiliar. So we start out with the most simplest organisms, and as they evolve, they become more complex through time. And what you may have noticed here is actually that there is an embedded timeline in this network. So this is an evolving system, that makes sense. We have a timeline that is embedded in this network. But that's interesting because the only piece of information we actually included here is coexistence. So did these things coexist? So it's really interesting that a timeline is falling out of this. But of course, it's an evolving system. So we also see this in our mineralogical networks, which is even more interesting. There's another way to visualize these evolving systems, and that is with taking time slices of these networks instead of showing them all at once. And that is, so that's what we're doing here. So each one of these time frames is 1,000,000 years. And you'll notice that there are certain large swaths of time where everything more or less remains the same. It's pretty consistent, you know, it's the same genera. But then you'll see suddenly everything switches. All of the former genera go away, and there's this whole new group of trilobites. And this punctuated event actually represents a massive faunal turnover or a mass extinction event. And actually, we were able to work with our colleagues, Drew Vicenti at Harvard, who's a paleobiologist, and we actually discovered, using network analysis, a previously unknown massive faunal turnover event late in the trilobite record. So that was really exciting to actually discover essentially what is a mass extinction event. So we're pushing forward. We're working with people like Chris to try to help us get more advanced in our visualization. So here you can see me playing with a virtual reality system in which we're using three-dimensional networks so we can really kind of dig in there and learn more about our data sets. Of course, there are many, many ways to visualize your data. You've seen a couple incredible ones today. There are also a lot of advanced analytical techniques and machine learning algorithms that you can use on the back end of your data. And so we're really excited to keep pushing forward in this data science direction with our research. And with that, I'll turn it over to Gina.